I'm not Deepika, but I'm here on her behalf, and she wasn't able to make it today. So I'm Sam again. I'm here to talk about observability in Ceph. So generally speaking, introspecting complex distributed systems is a giant pain. Client-level behavior, particularly with respect to performance, especially time-varying performance anomalies, can depend really sensitively on any subcomponent in the system. As such, it can be really handy to have a way to trace all of the involved components and associate all of the different sort of events for a particular I/O back together. So to that end, I'm going to be talking about the effort to introduce Jaeger distributed tracing to Ceph. I'll talk a little bit about how the various Ceph components fit together and how I/O requests work, and then I'll talk about how Jaeger can be used to give us insights into these processes in production. So for the fourth time today, Ceph has three components: clients, OSDs, monitors. Monitors not involved in the I/O path. Clients send I/O directly to the OSDs. So when we're doing an actual read, the client computes the location of the read using the cluster map obtained from the monitors to get a placement group, and then it uses the cluster map and crush to compute the actual OSD it needs to send the read to. And then it sends it directly to the OSD. For a write, same basic deal, but the primary OSD is then going to bounce it to the other two replicas for replication size 3, or 5 other ones if it's erasure coding. It'll wait for all of them to complete the writes, and then it'll and its own local write, and it'll respond back to the client. One thing that makes this somewhat trickier, though, is that a particular node will not typically read or write to the same object twice in succession. Typically, if you're, for instance, a compute node running a VM, you're going to be bouncing all over the logical block space for your RBD device, which means every 4 megabytes you're onto a different object, and therefore a different PG, and therefore most likely a different OSD and host. So if you see a performance anomaly in a client, it could have been any of the OSDs you've talked to over the past whatever period. So that complicates matters somewhat. In complex scenarios, an I/O could be slow for a lot of reasons. There could be a write that's still in progress and hasn't completed yet, and the read needs to wait for that to be stable before it can return, or it might return a write that didn't actually happen. The set of target OSDs might change due to a death or a failure or a recovery. You might be writing or reading from an object that isn't actually present on the OSD you're writing to because of a failure that happened deep in the past. It might be that one of the OSDs you recently talked to just happened to be badly overloaded. Perhaps it's a very popular RBD parent image with some block that just gets a lot of reads. Or it could just be faulty. It could be a disk that's on its way out and it's having a bunch of retries. So these things can make these sorts of problems really hard to figure out. This is a familiar pattern for anyone who's sort of worked on the sort of monolith to microservices transformation. The more different parts are involved, the more inscrutable any particular behavior becomes. So the current go-to solution for figuring out why a cluster is misbehaving is probably to email the list, at which point a helpful developer will tell you to enable debug OSD equals 20 and debug MS equals 1 on every OSD in your entire cluster, which will be not great. Sufficiently verbose logging is actually quite slow. The CPU cost is quite high because of the actual process of constructing the strings and sticking them into the log files. And with hundreds of OSDs, it's really hard to identify which set of OSDs you need to enable logging on without already having enabled logging. Moreover, as I mentioned, if you see a performance anomaly in a particular VM, it could have been any of the OSDs it's talked to recently. Moreover, it isn't necessarily the case that it was a single OSD that gave rise to the problem. It could have been a network link or many other things. But finally, the logs themselves are really not meant for users to read. They're meant for developers to read, and they're not real great for that reason. So it would be nice if we had a way of sampling particular requests across all of the OSDs, or it would be nice if we had a way of sampling a request such that all of the events for any particular request, if we did sample it, all show up at a central location to be analyzed. So enter distributed tracing generally. So the idea here is that at whatever the edge entity is, so for us the client, we assign a unique ID, and as that request propagates through the system, we ship along the context of any open spans, which I'll talk to about in a moment, so that every time we emit an event, we emit it with all of the metadata we need to later reconstruct it into the original request, allowing us to eventually reconstruct a call tree like the one on the right, containing all of the important events and spans that comprise the request. So I mentioned span a few times, and a span in this context is meant to represent, for instance, for a Ceph request, there are a bunch of sub-processes that we do. From the client's point of view, you sort of send the request off and wait for it to complete. But under that, the primary OSD read the request for some period of time. That would be a span. The request then spent some amount of time in the OSD's queue, and then spent some amount of time doing CPU work to construct the transaction to send down to its own blue store and to the other OSDs. And these spans you can sort of think of as nesting. So each one has an operation name, a start and finish timestamp, a set of sort of arbitrary key value pairs that represent span tags. These could be used to disambiguate reads from writes, or write size or read size, ways we can later refine queries to find out what exactly was happening during a particular time period. And for each span, we can also associate a sequence of events, which would be the span log component here, to allow us to sort of note important timestamps within the span process. And then we can also associate a set of these baggage items that will be carried around by the context as it moves through the system, so that later things can read useful information back off of the Jaeger context. So the particular implementation of tracing we're adopting is Jaeger. So the architecture looks something like this at a sort of a broad level. We have within each host process, this would be the OSD or the client, we have this Jaeger client that implements the Opentracing API. That client ships events off to the local Jaeger agent running on the node, and that Jaeger agent is configured to know how to find the cluster level Jaeger collector, which will then shuffle all of these events into a data store, in this case Cassandra, for later consumption by a UI and query subsystem. It also has this thing where it can do adaptive sampling. And what I mean by that is that we don't actually just want to run this on performance clusters or when we have a problem. Ideally, we would be running this all the time, so that you could look back over, let's say, the past day or week of data and do analysis on what the cluster was doing. That way you don't just have data when the cluster is misbehaving, you also have behavior or data when it's behaving properly. It also means you don't have to go and enable tracing when you observe a problem. You'll already have it. But to do that, you need your sampling to be fairly invariant with load. You need it to be the case that when you multiply the amount of load in the cluster by 10, you don't just get 10 times as many trace samples, because you might overwhelm the backing store. So Jaeger will feed back information that allows it to dial down the unique IDs it will choose to emit events for based on the overall load, and it will ensure that all of the components are able to emit events without overwhelming the backing store. So to make this work, of course, the main component of the project would be annotating the Ceph code, both the client and the OSD, and other components to actually do tracing. So this is sort of a code sample for how we set up the tracer within, I believe, the OSD. Jaeger can be configured with different endpoints, which is important because different environments will have different endpoint setups. For actually adding a span, in this case, we are creating a span under the overall OSD sort of request processing span that marks a particular flag point span. So this is a thing that already exists in Ceph. If you do a Ceph dump historic OSD ops or something, you'll see these sort of JSON dumps of ops and sort of timestamps at which different events have happened for each op. So what this does is take that a little bit further, and for each of those possible flag points, it will also dump to Jaeger a span representing how long it's spent there. So this would be read off the wire, went into the PG queue, started processing by the OSD, got submitted to BlueStore, that kind of thing. And then for each of these spans, you need to call finish. So there are a few categories that the current implementation does have set up. We have one representing the lifespan of a PG op item as it goes through the PG queue, and we have spans representing the do request and do PG op components of the processing pipeline, as well as the aforementioned flag point spans. So here we can see the sort of Jaeger UI with some Ceph data loaded into it. Each of these points represents a submit transaction begins span. The x-axis will be the point in time at which the span started, and the y-axis is the duration. And you can already see here a fair amount of variance in how long these things took. If you hover over the points, you can get more information, including the duration. And if you drill into a particular span, you can see some of the metadata I mentioned earlier. In this case, this is an NQOP span. And for this particular message, you have the epoch at which it was enqueued and the priority and cost associated with this op. Those have a bearing on how the queue behavior works. So here we can see 3 different spans associated with the same parent. So this would be the same request, just 3 different points in time. And across the top, I believe those are the sort of point in time durations that those spans represent. There's also experimental support for showing sort of the parent-child for visualizing the parent-child relationship that is useful for understanding how it all fits together, especially if you're new to the data set. So why did we choose to use Jaeger? So like I said before, we want to be able to run these sort of sampling strategies in production all the time, at least for a commonly configured Ceph cluster. So it's important that we have this adaptive sampling implementation and feedback process. Jaeger also has decently high performance UDP sample collection, which means low performance overhead. And between the two of those, we should be able to run them all the time. It also implements the Opentracing standard, so even if there does come about at some point in the future a better implementation of the sort of trace event aggregation system, we ought to be able to use the same actual annotations within the code, which arguably is the largest investment. And it's backwards compatible with Zipkin, which was a previous well-known and I think fairly accepted solution to this problem. So the current status is that the current implementation is still in a pull request, pending some work integrating a few of Jaeger's dependencies into Ceph's CMake system. But there are annotations for most of the important bits of the OSD I/O path. So future work, of course, will involve testing and looking for performance bottlenecks in areas where more annotations would be helpful. And also instrumenting other bits of Ceph, particularly RGW and BlueStore, I believe, still needs instrumentation. So that's all I've got. Any questions? It's not a huge room. We can probably hear you.
Ceph specific.
It's Ceph-specific. Jaeger isn't. Jaeger isn't Ceph-specific at all. Jaeger is an existing project.
Yes, I know,
as is
but the whole logging thing, right? It looks like that other system can benefit from it.
Okay, so Jaeger is a whole separate project. That's not our project. That's a separate thing that exists in the world. Same with the Opentracing API system. That's a different thing that anyone can adopt. But the actual instrumentation is actual modifications to Ceph code, because you need to go into whatever system you're instrumenting and go say, yeah, I mean, all systems have writes, right? But ours has one really specific message flow, And you want your annotations to match how the system actually does its work and which things are likely to be slow and which things aren't. So some things are general, and those things I think are the Jaeger Opentracing bits, but the actual annotating code part is a little system specific, I would say.
Thanks.
If that makes sense.
Do you have any like real-world examples of statistics of debugging problems with the Jaeger and Opentracing? Like, and yeah, what are the numbers? What is the most?
I don't.
Like, okay.
It's not quite merged yet, so yeah, we'd have to ask Deepika, but I believe that's essentially the next step. I can tell you hypothetical examples of scenarios where it would be so good. So basically any situation where you have a faulty network link is very hard to figure out from logs. Because what it looks like from the client side is a client is occasionally slow for no reason, right? So to figure it out, you have to enable logging on that client, get the logs, grep it for, assuming you're a developer who knows how the client logging works, for the log lines that indicate where the thing began and end, figure out which ones were slow, then go back to the logs and figure out which OSDs it was talking to by, again, looking at different log lines, then enabling logging on those OSDs, waiting until it happens again, then looking at the messenger logs between them and figuring out why, right? But if hypothetically you had logging on this whole time and the sampling rate were high enough that you had a decent probability of catching one of them, then what you'd see is spans that looked really normal for all of the storage components on both sides, but the network send and network receipt spans would be really big occasionally, but only on certain links. So that's kind of what we're looking for.
How much does a trace point cost in terms of microseconds or cycles?
I don't know.
Thank you.
But the more practical version of that is I believe the way Jaeger is structured, and don't quote me on this, is that the relationship between the client bit and the agent bit is like an in-memory lossy buffer. So if you emit too quickly, it's not going to slow down the agent, it's going to drop samples. So the common case is you simply write in memory to a shared buffer that the other side picks up. So it's not that expensive. Certainly it's nothing compared to writing a log line.
So what I'm getting is that this agent library will create a thread internally.
I believe actually that's a separate process. I believe all of the trace points, yeah, I should probably stop talking before I just start lying. But you can certainly imagine that it could work as a shared in-memory buffer, where you have a different thing that does the network stuff on the other side in a separate process that can lag if it needs to.
I mean, for us, sorry, we have a bit of time, so interrupt me if I'm too long here. I'm coming from Samba, and we have thousands of processes for busy systems. And so these things actually matter.
Yeah.
If we have heavy client libraries embedded into or linked into each process, or if if everybody spawned another thread, we're going to suffer.
So it doesn't have to, again, I don't actually know how Jaeger works, but I know for LTT&G, for instance, you don't spawn a thread per thing that does tracing. You spawn a number of shared ring buffers, and when you hit one of these trace points inside the client code, someone tell me if I'm lying, it emits like structured things into this shared memory region, and the other side either consumes it fast enough or it doesn't. If it doesn't, then it drops events, but it never slows down the client process, and they don't all start their own threads. Does that make sense?
Yep. I can just imagine it's very, very difficult to get this right when you have to expect crashing processes.
Well, as long as it doesn't crash the agent, it's not so bad. But actually, in this case, we could start an agent per OSD. It wouldn't be a big deal.
Yeah,
but with Samba, if you have a multi-process model, I can see how that would be tough.
Any more questions? Okay, well, thank you, Sam.